So after finishing the topic on plane areas, now we'll extend this topic to finding the volume of solids of revolution. Now, the very reason that they are referred to as the solids of revolution, it's because you're going to revolve. So revolution, you're going to revolve a particular chosen differential area on an axis of rotation. So the corresponding volume that will be produced is the volume of that particular solid that you are determining. So in here, we have actually 3 different methods to use. Now, the ease of using these methods really depend on the user and depends also on the volume that is to be determined. So as to whether you're going to use the disc method or the cylinder method or the ring method, that's really dependent on you. But as long as the method that you have chosen is appropriate for the volume that you are to determine, then you won't have a problem with that. Okay? But anyways, in terms of the principle, I try to make it very simple and fundamental. That way you can apply it to whatever scenarios later on you will encounter under this particular topic. So as for learning objectives, so you are to determine the volume of revolution using the disc method, the washer method, or the shell method. So the problem will not really indicate what particular method you will use. It really depends on you. You will be taught on these techniques, and as to whichever technique is appropriate for the volume that you are to determine, then you are the one who is using, or you are the one who is choosing it. Okay? Now, you see these solids, they are irregular in shapes. So some are regular, like this one, this is regular, so uniformly shaped. This one is not. Now, actually, they are composite solids if we are going to apply the concept of volume of solids of revolution. Why? Because this one can be that of a small cone, while this one is another cone in which you have a hollow part in here. So you have 2 composite figures, one that of a smaller cone and another, this one, a bigger cone. This one is not a composite figure. This is just simply what we call a disc. Now, this solid, sorry, you may not be able to see my arrow. So this one is a composite figure, as I have mentioned. This yellow thing is the disc, but this one is uniform. So it's just a one figure thing, a uniform volume. Well, this one is another composite figure. You have here the cylinder as based on what you have learned in your senior high and in your high school. And this one is an irregularly shaped solid. So the volume here is also irregular. So another one is in here. So in determining the volume of this composite solid, you may take the volume of this, determine the volume of this separately, followed by this one and this one, and add them. That would be the volume of this particular solid. That same applies with this. So you have here a disc, bigger disc, and you have here a smaller disc, and you have here a cylinder. This one is also a cylinder, but this one is irregularly shaped. Okay, so that depends on the particular equation of the curve or of the line or of that particular area that you're going to rotate on a particular axis. That way, you can produce this particular solid. But nonetheless, determining the volumes of this irregularly shaped solid and this one which is regular is anchored upon the fundamental concepts of the volume of solids of revolution. Okay? If the solid is regular, you have the standard formula in your solid mensuration or in your solid geometry in high school. So you have that formula for a disc, you have that formula for a cylinder, you have that formula for a cone, and so on and so forth. So you can use those when the solid in question is regularly shaped. But if it's irregular, then that's where your integral calculus will come in handy. Now, let's go into if I'm a student, and if I recall the time when I was taking up this subject then in college, I find this method the most friendly of the 3 methods, the disc method that is. However, of course, this has conditions that has to be met. But in terms of understanding how this method is to be used, it's quite easy for me. So in my viewpoint then as a student, I find this easier compared to the other two. So when we speak of a disk, it need not really be a regularly faced disk wherein you have a circle for the face and you have a corresponding thickness. So that circular area that you have, once that particular circular area has a thickness, then what you will have is a disk. Or if it's that really long, then what you have is now a cylinder. Now, if you cut a sweet potato, in this case, these are irregularly shaped discs. But these are comparable to volumes of this. This one, this cut portion. This cut portion is a disc. This one is another disc. So if you intend to find the volume of this irregularly shaped potato, you may actually cut through different discs and then add up the volumes of each disc from this particular, let's say, if this is your X here, from this particular point here and to in here, in terms of your limits of integration, that is. So you now can determine the volume of this irregularly shaped potato using the disc method. But what is really the disc method? So imagine this is the area in question. So let's say if your potato, if you cut it in a cross section, you'll divide it into, let's say, for example, 4 quarters. This would be one face of that quarter. If you intend to find the volume of this particular quarter, this entire thing, you will have to select, again, a differential area that will uniformly represent this area that you will rotate on this axis X. Now imagine, you can close your eyes, imagine that this area that we have, this differential area that we have, will be rotated around this axis X. So what you will be forming is a disc, right? Daw piso, nga damol, because the thickness of that disc will be this thickness. Okay, let me just annotate. The thickness of that disc would depend on this one. So if you rotate it in here, or just like the way it's written here, if you look in this particular side, what will be forming is this one, the disc. Be forming this one, a circle. So that's the plane area. But once this circle is multiplied, once this circle that we have is multiplied by the thickness of this circle, what you'll have is the disc already. So this is actually your dx. The dx is this one. Okay? Now we know that the volume from high school is equal to the area of the base times the height. Okay? When you speak of this, when you speak of cylinder, and since we're talking about this method, the volume is the area of the face, the circular area of the face, times its thickness. So that would be the height or the thickness of that thing. So in this case, if I have this rotated here, if I have this area rotated here, the area will be this area here. The area of the face will be the area of this differential element. This is the radius. And if I'm going to multiply it by pi, the corresponding thing that I will be forming is this circle. A circle of radius r. Pi r squared for that will be the area of this face. And that face is this, the one that I have checked. As to the thickness of this face to make it a disc, that would be this differential dx. Now, if you take all of this, you cut another differential area here, rotate this area on this axis, you'll have another disc, right? Then another disc here, another disc here, if you cut it until you form this figure. It will look something like this, but if it's connected smoothly, it will look like something like that. It's a solid now, just like the potato that was shown to you a while ago. So it's a solid in which you determine the figure out of making discs. You cut it into disk and then add up the volumes of this disk. That is why you have the term, the disk method. So using your calculus in this sense to find the volume of this irregularly shaped solid using the disk method, you have this formula. The volume is equal to pi r squared, the area of the circular face times the height. This is now the volume of the said irregularly shaped solid. As to what would be the limit of integration, that would still be the same as the area concept that we used. This area that you cut through a selected differential area is bounded by A and B. So it's dx, so it's A to B. So you're going also to write the limits here, A to B. You get it? So the volume of this irregularly shaped solid is equal to pi r squared. Now, what is this r? You place here r. What is that r? So I'll cut it in here, huh? So this is dx, and this is the r. What is this r? Just like in the concept of plane areas, that would be the equation of this curve. That's your function of x that is written there. So that would be the equation of this curve and the equation of this line. The equation of the line, or specifically the equation of the x-axis, is actually y equal to 0. So in this sense, excuse me class, I'll just pause. So these are the r that we have, the radius of the face, the circular face of the disk would be then, if I will annotate, that would be the y of this point, which is that of the curve, f of x. This is the y of the curve minus the y of the x-axis. This is your x-axis, which is y equal to 0. So as you could see here, your dv, to take the integral of that, that would be equal to the v, is equal to the integral of pi r squared. What is the r squared? That would be your yc, supposed to be yc minus y of the x-axis, but the y of the x-axis is 0. So you simply have v equal to pi f of x squared, and then you have this dx. And you are going to integrate it from, so you can see these limits, A to B. You get it? So when we speak of solids of revolution, just like what we have discussed in plane areas, you always choose the differential element first, appropriate to the volume that you are to determine. In this case, class, your differential element, your differential area is perpendicular. So notice, in this method, it's perpendicular to the axis of rotation. So you're going to rotate the chosen differential element on a particular axis to get the volume that you desire. So in this case, if you choose dx, it's perpendicular to the axis of rotation. Okay, perpendicular, you know what perpendicular is. It makes right angle with the axis of rotation. So I hope you can visualize that what you're going to form is this particular irregularly shaped solid. Okay, this is one scenario wherein your axis of rotation and your chosen differential element are attached to each other. Your differential element is perpendicular to the axis of rotation and it is attached to it. You're still going to form this disk, several disks, which when you will connect all together will be the volume representative of the solid in question, whatever that solid is. Okay? Now, before I continue, do you have any question in this part? So volume will always be area times the thickness or the height. Oftentimes, that thickness class, especially when we talk about the disk method, is the differential. It's either the dx or the dy. You chose it just like the way you chose the appropriate differential in plane areas. It should be uniform for the area in question. Okay? Any question? Okay, I'll clear my markings here. Okay, there is. Now, we go to the next one. This is still the this method. However, very closely look. Your axis of rotation is not the x-axis. I will annotate here so you can clearly see. This is your x-axis. Okay? Now, this time, this is your x-axis. Your axis of rotation is below the x-axis. So, you see here, y is equal to negative k. So, this line, which is your axis where you're going to rotate your differential element, has an equation y is equal to negative k, where k is any constant. Negative in the sense that it lies below the x-axis. Now, in that case, how will you determine the volume of the solid of revolution? So, the area that you are to rotate on this x-axis, if you're going to use this method, will be the blue shaded area. How will you write the volume expression for this? So, simple. So, your volume is equal to, we go back to the premise again, the area times the thickness. Now, in terms of calculus, we'll write here the integral of, so the area in question has to be pi r squared. It's always the face of the circular disc. So, circular. So, if this is the chosen differential area, and actually it should be the chosen differential area if we use this method, and this is the axis of rotation, we know that this r squared is very important. It's very important. It should be correct. So we'll have to write it later. But this is still dx because it's vertical. So I'll place here dx. And you notice that this is bounded by these two vertical lines. If I'll place vertical lines here, and that would be from A to B. So what is very crucial is the correct expression of the radius. If I'm going to ask you, okay, let's see, what is the length of this radius of yours? Because if you're going to rotate this differential area on this axis, the blue axis below the x-axis, this entire thing will be your radius. Okay, that would be the radius of your differential element. So you will form a circle with this radius. How would you write the radius expression? So I will have b equal to, I can write the pi before the integral symbol. I can separate it because it's a constant. But I need to correctly write what is r squared. How do you think I should write the r squared? Anybody who can try? What should be the appropriate representation of the r squared? If this is the equation of the curve, and this is y, and that y is the function of x, it's a function of x as stated here. And how should I write the expression of the radius? How should it be? Your axis of rotation is the blue one, not the x-axis. But what is common between these two, since we're using this method, is that your differential element or your differential area is perpendicular to and attached to your axis of rotation. Nagatapik siya sa axis of rotation. Kag naka-attach to siya, wala siya nagahang. Wala siya galupad. Because later on, may ara, nga wala siya nag-attach sa axis of rotation. Okay. What is the appropriate expression for the radius in this case? You can write, okay, I have here f of x minus k squared. Length minus x is equal to the radius. Okay. If you could see what's written on the chat box, that is very good, JJ. Your radius here will be f of x minus negative k. When you subtract something that is negative, it's like adding it to the original function, right? So what JJ wrote there is that your radius should be squared, and it should be the function of x, the y of this point, and the y of this particular line. And what is the y of that particular line? That is negative k. So in truth, your radius here is f of x plus k. The entire expression should be squared. And you have here dx. Very good, JJ. So, amo na siya ang radius niya. Iskitan, awon mo na lang sa figure ho, ano ang radius niya kung patiyugon mo ini nga differential area sa diri nga axis of rotation. That would be from here to here, that's your function of x. Kulang na siya. Wala ni ma-include ang sadalom. Ano ni sadalom? That's your negative k. But since you're considering the entire length of this, so what's the procedure in differential area or in our plane area topics? Highest point minus lowest point. Highest point is function of x. Lowest point is negative k. So function of x minus k. So that is why it became plus. And true, whatever is the absolute value of this distance here, it's actually negative because it's below the x-axis. But you need the positive value of that because you need to add it to this length. So function of x from here, from x-axis to here, plus this k here. That would be the entire radius of your volume in question. Do you get it? Do you have any question? Okay, so if there's no question, I will proceed if there aren't any questions. So we'll just clear the markings here. So we'll proceed. You can also have your axis of rotation above. So, ari na siya, class. Sa babaw na siya. This differential element is situated on the axis. It's attached still on your axis of rotation, but this axis of rotation is above the x-axis. So what is then the radius that we have here? So allow me to annotate. This is still your differential of x. Notice that your axis of rotation is still perpendicular to the differential element chosen, the differential area chosen, and your differential element or area is attached to it. So, nagatapik siya dira. So, what is this point? And what is this point? So, pariho lang din siya gyapon sa plane area. So, if this is your R, the area is pi r squared. And what is your r? That is the function here. This y minus this y here. What is that y? That's the k minus k squared. Still have dx. And it would still be having the limits a, b. Why is it minus? Because this axis of rotation, you're going to rotate this particular differential element. Visualize it that you will rotate it on this axis to form the solid. So it will form this figure as well. Amo man ni siya gyapon ng shape. Okay. Only that your axis of rotation is this one, above the x-axis. So subtract. Because you're only interested in the circular area of the face wherein this is your radius, not the entire thing as dire. Why? Because this is not your axis of rotation. Your axis of rotation is this one. So you have pi r squared dx. You get it? Now, what about this? if the chosen differential element is something like this would still be a dx. What's the highest point here? That would be the k, right? The lowest point is the function of x. Your differential element, notice, is still attached to this axis and it's perpendicular to it. So that is true for all volume of solids of revolution solved using the washer method. Ang unang requirement, differential area should be perpendicular to the axis and is attached to it. Okay, para solid siya, wala siya sang buslot, wala siya sang hollow nga part. So what is this length here? That would be your k minus f of x. Since it's pi r squared, it's squared here. Then dx. Then you also have this limits of integration a to b because you have dx. Do you get it? Any questions? Now, this is when your differential area or your differential element is, shall I say, vertical. All of those are vertical, right? What if it's horizontal? We'll just have this annotations cleared. What if it's horizontal? Okay, you have this one. You're still using this method, but your differential element now is horizontal based on these curves. So your curves now are x as a function of y. Why is it x as a function of y? Because your differential element chosen is horizontal. So these are all dy. These are all, so included na siya dy. This is dy. This one, if this is your differential element, this is also dy. Okay, same premise. Pi r squared, the area of the circular face times the thickness. So the thickness are all represented by dy. Okay? Now, you still have the pi because it's a requirement for the area of the circular face of your disk. Now, the radius is the next thing that you will determine. So in this case, your differential area is attached to this axis of rotation, which is the y-axis. So your axis of rotation is the y-axis. So the width, so the length is dy. So the width of this differential area is actually the rightmost point in this differential area minus the leftmost point. The y, or rather this y-axis has an x equal to 0. Okay, your x here is equal to 0. So you have here this minus this. And what is this? That's your x of y. A function which is in terms of the y. So you have x of y minus this one. Your x here is equal to 0. So minus 0 lang. So you have x of y squared. If this is your axis of rotation, the y-axis is your axis of rotation. What happens if your axis of rotation is on the left of the y-axis, like this? So if you notice, its equation here is negative k because it's situated on the left side of the y-axis. So negative ang imo x. So pariho lang gigyapon kay na. Your differential area that you have drawn, which will be rotated on this axis, will have a radius which is the y of this point, the farthest to the right, minus the y of this point. And since this is negative k, the x of this point rather minus the x of this point, this is negative, so it will be positive. So x of y for this one plus the k. So this is the entire radius. It's the entire radius. Iski hindi ka pa maggamit sa mga minus-minus nga concept, common sense will tell you that since this is the equation of the function in terms of y, from here to here, kulang na siya sa length nga radius na kinahanglan. Tadugangan mo pa sini. So what is this? That's the k. So k plus the x of y, you have to square it because the entire thing is the radius. In here, your axis of rotation is not on the left of the y-axis, but to the right of the y-axis. So this is still your differential area. So the x of y of this minus the x of y of this. And what is this? That's k. So you have x of y minus k. So the radius here is shorter compared to the radius in here, which goes beyond the y-axis because it's to the right of the y-axis. So minus siya. Squared gihapon. As for this radius here, so this is your axis of rotation. What is your radius in this case? So the same thing, the axis of rotation. So you have the farthest most point to the right minus the leftmost point in your differential area. Mugine premium concept class, ang pinakataas na point sa differential area minus the lowest point. If it's vertical, if it's horizontal, the farthest point to the right minus the one on the left. So this one has an equation of k. This one has an equation of x in terms of y. So that is why you have k minus x of y. Of course, you still have to square it. That would be the radius. It's the radius of this differential area which you rotated on this axis of rotation. So, ma-imagine nyo man, kung tiyugon mo ni siya nga area, what you're going to form is a disc or a 1 peso coin. Okay? So, several coins here of different diameters, you add up, you'll form this irregularly shaped solid using the disc method. There are two things that you need to determine in the disc method. Number one, actually it's the same for all methods, but for now for the disc method. Number one, the axis of rotation and your differential elements so chosen should be perpendicular to each other. Perpendicular, gina siya, perpendicular. Second, your axis of rotation and your differential elements should be attached to each other. So there shouldn't be any space in between the axis of rotation and your differential element. That's the requirement when you use the disc method in finding the solid of revolution. Okay? Any question? Any question? Okay, sige. Let's see if we can end with a sample problem here on this method. Find the volume of the solid obtained by rotating about the x-axis. So you're going to rotate about the x-axis. This is your x-axis. And this is where you're going to rotate the region under the curve. So the region under the curve. And this is the curve y equal to square root of x from 0 to 1. So the curve y equal to square root of x from 0 to 1. So if you're going to use the disc method, your differential element here will be vertical, dx. If this is your axis of rotation, notice that it's perpendicular to it. And this differential element or area is, in terms of representation, it's uniform for the region or for the section. Okay? So if you're going to rotate it, this will be the volume that you're going to form. I hope you can visually imagine it. So the differential area that was drawn here is this one. If you're going to rotate it, you will have this disc. You will have several discs rotated and you will form this particular solid figure. Okay? Now, since the solid lies between 0 and 1, that would be your limits of integration, starting from 0 to 1. You have to start with the expression of the area of the circular face, and of course, you have the dx. The area of the circular face that we have is actually pi, because we always have the area of a circle starting with pi multiplied with the square of the radius. So this should be this one. The x of this minus the y of this rather minus the y of this. This is y equal to 0. So this one will be your y equal to the square root of x. So before, I can write here 0 to 1, you have pi, and you have here the y, which is square root of x. So I'll place here a square root of x, and I need to square it. Why? Because we have pi r squared, and we have here dx. If you square a square root, you will have this one, right? Then you do your integration, you will have it as pi x squared over 2. Your limits is from 0 to 1. So when you substitute 0 as the lower limit and 1 as the upper limit, your answer is pi over 2. So cubic units. If in area, in plane areas, our answers are always square units because it's area. In volume, we place it as cubic units. So this is the answer, or this is the volume of this particular solid figure using the disc method. Do you get it? You have any questions? No questions? Okay, let me see. One is none. Okay, let's see if I have another one here. I'll just clear my markings. This one, your differential area is this one. And the differential element chosen is horizontal. But before that, what we have here, find the volume of the solid obtained by rotating the region bounded by, so what is that region? Y equal to x cubed. Okay, I'll just borrow a few minutes. So this is your region, or that's the equation of the curve. Y equal to x cubed. It's bounded by y equal to 8. So this is the line, y equal to 8. And you have the x equal to 0 line. So that would be the y-axis. So this is your x equal to 0 line. So the area that has to be revolved around the y-axis is bounded by this line, y equal to 8, x equal to 0, and this curve, y equal to x cubed. Or we can say here that x is equal to the cube root of y, if you express x as a function of y. So find the volume of the solid obtained by rotating the region bounded by this geometric figures about the y-axis. So you could see in here that the appropriate differential element, since this is your axis of rotation, if you intend to use this method, would be horizontal. Amo gini siya ya? Because you want to use this method in finding the volume of the solid if you rotate this particular shaded area in blue on the y-axis. So this is your dy, that's your dy. So for your radius here, the radius here would be the y for this part, for your curve here. So that would be the cube root of y, or the x of the curve, minus the x of this line. So you see here, pi times the cube root of y. So the reason why it's already y raised to 2/3 is because originally, class, it's written as pi. Your x for here, in terms of y, is cube root of y. But you're going to square it. Anyhow, when you subtract x equal to 0 to x equal to cube root of y, that would still be the cube root of y. So you square this one, and you have dy. From your algebra, you can write the cube root of y squared as y raised to 2/3. The rest is just very easy because it's just power rule of integration. So you integrate using power rule. This would be y raised to 5/3. And you will have it multiplied to 3/5 because this is actually over 5/3. And you have the pi here. When you substitute the limit 0 to 8, now why is it 0 to 8? Because for this blue shaded region, you start with y equal to 0 to y equal to 8. You use y because the thickness of your differential element or area is in terms of y. So your limit of integration is also based on the y coordinates of your geometric figure that bounds your area. So it should be 0 to 8. Your answer would be 96 pi over 5. So meaning, this area, when rotated to this axis, will give you this volume. Amo ni iya itsura. And this is the value of the said volume. Do you get it? Do you have any question? Any question? None? So I will clear my markings here. We'll update our schedule later. We'll post it in our GC again. Okay, so next meeting, we will be discussing the washer method. So you see the washer, it has a hole inside resembling that of a washer. And the shell method. So we have two methods still to be discussed on solids of revolution. Okay, class? I will now stop in here.